I think we're all set. Welcome back, folks. This is the end of week 14 out of a 16-week semester. I have a bunch of announcements scattered out through here, but any questions from the class first to start us out? Okay. Well, with where we're at so far, 7.4, we just have a really short problem that we need to get through, dealing with Fermat's little theorem. Then section 7.5 is going to be where the course is going to culminate. Really, because of a lack of time, this is a good stopping point for us. This is a great section as well because it's a good opportunity to kind of pause, take a look into some older information. For example, these sections here that are pulled up on the PDFs are all relevant to that last final section. So in a certain sense, section 7.5 is kind of reviewing for the final exam at this point. And the other announcement is I'm going to begin grading the exams over the weekend, really starting on Friday. It's kind of like a pseudo weekend day these days. And if you did take the exam in class and you know you might not be in class next week during closed week, send me an email and I'll make sure after I grade the exams to get your hard copy scanned and sent over to you. I intend to really send it back to everybody, but if you send me an email, it just puts you on the top of the list. I'll get it sent over sooner. Well, any questions at all, folks, with where we're at so far? Okay, well, we're just about done with the course. Today, we're going to be doing kind of a light topic in 7.4 and some really interesting applications in 7.5 on cryptography. I can tell it's a new word for me to say out loud. And then next week, we're just going to finish up what we didn't conclude on in section 7.5, shouldn't be too much, and immediately convert over to reviewing for the final exam. So that's where we're at so far. And we left a week ago from today, right around, not here, at the end of the document. But this is a good place to start. It's kind of busy, but let's focus on this part right here. This document was all about collecting a new operation, a sort of pseudo division in the set Zn, where we're multiplying by a multiplicative inverse. So we say A times A inverse is equivalent mod n to 1, tells us that we have the right inverse for A itself. And there's a whole lot of different theorems about that inverse, but the major ones we're focusing on are the computability of that inverse given a set such as Zn. So the really fast check we did on a couple problems was to find 5 inverse, or to verify 5 inverse equals 3 in Z7. We take 5 times 5 inverse, but then 5 inverse was 3, so we took 5 by 3, getting 15, but mod 7, that's equivalent to 1. That forms the verification, and then from there on out, we were studying Zn a little bit more closely. This lists out all of the inverses once we put them in a multiplication table. We couldn't do that for every single problem, so we observed we need some theorems and a good algorithm to help us out. That's the inverse algorithm that will compute the inverse of a value if it exists. And then as a bonus, this theorem gives us the existence of the multiplicative inverses. We're interested in, let's see here, relative primality between the numbers. So as a immediate consequence, in Zn, if n is prime, then every element inside that set other than 0 is going to have an inverse. And this is the method or algorithm that we're going to use to compute them. Well, that's our really short tour of what we did on last Thursday before getting into Fermat's theorem. And so now for Fermat's theorem, or little theorem as it's called, to not get confused with the other theorem he's infamous for, goes like this. It says, let P be a prime, and then pick any element in ZP, again, non-zero, since we don't have any inverses for any zero element. Then if we take A to the power of that prime minus 1, it will be congruent mod P to 1. So that's an interesting statement altogether. It is giving us a lot of interesting information. It's kind of telling us as well when we look into that, if A to the power of P minus 1 is congruent to P mod 1, that would also mean that a power, let's factor out, say, 1 factor from A. That's doable because if P is prime, it's 2 at least. Then multiply it by A to the power P minus 2. It'll still be congruent mod P to 1. And so that's telling us we have an automatic inverse in a certain sense. So A has a to the power of prime minus 2 as its own inverse. Let's make that a conclusion here. So now going this way, A inverse is congruent mod P to a to the power, or let me say this in a better way, that would be a congruent mod P to 1 over here. Mixing up notations, I should just say A inverse is equal to directly a to the power P minus 2. That's one just direct consequence of Fermat's theorem. But the comment down below is also telling us the major thing or major role in Fermat's little theorem is it's the mathematical underpinning that proves that RSA public encryption system by these three gentlemen here really works, that a method we're about to describe can encrypt a message and can be de-encrypted every single time. So that's the major role of this theorem. But within the section 7.4 notes, just think of it as more information about inverses inside of ZP. Well, we're going to try out to example 4 just to get a feel for the theorem, see what happens when we do take a prime 7 and values inside of ZP. So before we give that a try, any questions at the moment? Okay, let's try this out for when A is 3, first value in the list, we have a prime 7. We want to check that it's in ZP, but all these values are between 0 and 6, so it would absolutely be in ZP. Recall, just for the sake of remembering what that was, because it is a weird new algebraic structure, Z7 in this problem is going to be 0, 1 through 6. So these are really the only values we could have given. Well, these are some of the major values we could have given. We can't give a value with A as 51, for example, and check it on Fermat's little theorem. We have to be constrained inside that set. Then we take A to the power of the prime minus 1. So A power 6 is going to be equal to 3 power 6. Compute this mod P, or let's say what the prime is, mod 7. This part right here is just where we said congruent mod P to 1. Sort of checking that part right there. It is kind of an interesting computation, but we have some algorithms for this. Let's give this a try, just because we have this as a tool. Let's call in our mod and div algorithm, give it 3 power 6 and 7. Take just the output 1, so we get the modulus part. And sure enough, it tells us it is congruent mod 1. We did it in a kind of a weird way. We didn't compute this exactly. That's okay. We're going to have some practice doing that later on, because sometimes these algorithms, it's just not as built up as we might need it for some of the computations we're getting into. For example, what if we went 3 power 60 mod 7? It's going to be a problem. RStudio is working through it, but it might eventually halt on its own or just cause some RAM issues on the desktop. Might as well terminate that. There's a built-in modulus operation inside of any good coding language. So if we try, say, 3 power 60, this is how you can call mod inside R. 3 to the power 60 mod 7 gives an immediate warning. This is kind of interesting. Probable, so they're pretty sure this is not going to be the right value, even if they gave it to us. Probable complete loss of accuracy in modulus. That's a heck of a statement, right? And the modulus operation here is really well built up. R is built on top of C and Fortran, for example. It has a lot of great routines. So that's where we're going to need this list right here. We still have to compute these things, but we need to start breaking them down by hand. And this gives us one major tool, part 4 right here. So even though we didn't need it on that problem, let's try it on the next, using this as a tool, just in case, because in the next section, just in case we see these kind of mod values, because we will see them in the next section. Things that are just a little bit out of reach for the standard operations. But on this one here, through mod and div, we've got an immediate computation. This is using mod, and div algorithm. For a is 4, let's try it using modular arithmetic. So these values down here, just for the sake of practice, more than anything. When you go to do them on the homework, any method will work out just fine. Well, any questions at all, folks, with row 1 on this one? Okay, let's try it out again. This time we're grabbing a is 4. We take a to the power 6, same exact prime as before. So now we're looking into 4 power 6 mod 7. And, it's definitely doable by all of our tools we have so far. But let's use this property like we said, for the sake of practice more than anything. So one way you might be able to do that is the power of 6 is just kind of sometimes inconvenient to deal with, especially if that order of magnitude is really high. But we could factor the power lots of different ways. Just let's go for anything that seems convenient. 6 factors as maybe 2 by 3 should do the job. Definitely, that's kind of the only factorization when you think about it. So I'll rewrite this as 4 power 3 to power 2 mod 7. So that's going to be our computation. It tells us we can now do the modulus of 4 power 3 on the inside. That's the point of that portion right there. So kind of a neat little trick to just cut the number down to size. So we'll go and say that this is equal to 4 power 3. Let's write that in. 4 power 3 is 64. Mod 7 to the old exponent power 2. Then mod 7 again. So the 4 power 3 became the 64. The power 2 here just gets inherited back down. And 64 mod 7, that's a little bit more doable, right? Let's see. Well, 7 by 9 is 63. So 64 mod 7 is an automatic 1. That means this is just looking at a 1 power 2 mod 7, still a 1. But I probably would want to double check that. Let's see what the hardware says about this. Mod and div, or let's do this one. Why not? It got called up first. We're doing altogether from that line 4 power 6 mod 7. And yeah, we do indeed get a 1. That's encouraging. And doubly encouraging because Fermat's theorem says we have to get a 1, right? So we're definitely on the right track. Well, that's verifying 2 different cases, 3 and 4. Let's try one more just for the sake of completion. Any questions at all, folks, with where we're at so far? Okay, let's finalize this last one and say if a is 5, let's use the mod and div operation again. This was more a demonstration of what we're going to do in the next section. We'll take a power 6 as in the theorem. So now it's 5 power 6 mod 7. And 5 power 6 mod 7, well, we can handle 5 power 6, I'm sure of it. So let's give it a try. 5 power 6 mod 7 does indeed come out as a 1. So that's our third verification through that Fermat's little theorem. Well, we did it, folks. That's the conclusion of section 7.4. Kind of weird to leave such a short problem at the end, but at least it gave us an opportunity to wrap back and review inverses before delving into the very next section. Well, before we jump into that section, any last questions or comments with any of the work here? Okay, let me pull that up next. And this is, again, kind of an interesting section because there's seems to be a lot to do, but there's more information here about setting up the problem than the actual computations that we have to do in these notes. So even though it's 4 pages long, it indicates there's not a whole lot of computations, more just kind of absorbing all the information about what is this problem when we say cryptography, what are we getting into? To take a tour through the notes before we jump in, example 1's kind of a warm-up problem. What we're trying to absorb is this information here through this diagram. Once we get a good handle on what all this is saying between Alice, Bob, and Eve and their roles they're playing here through this problem, we'll be able to turn into the RSA crypto system. It's not the exact crypto system that's applied in practice, but this is the textbook version of the crypto system. So this is what it's really built upon, and then a whole bunch of extra security measures to make it more hard to defeat as well. So we'll go through the process of key generation, encryption, and this is the hard phase, it turns out to be, the decryption phase, where we have to do something that is a power that could be really, really high, mod something. That's where we're going to be using this tool quite a lot, because the hardware really does fail if we try to use it directly. Unless you just start redefining a better modulus problem or syntax for this that can handle higher values like we're looking into. So that's the idea of the notes. We'll look into kind of a silly problem where someone's trying to send a PIN number securely over the internet, and it has to be received without anyone listening in. This is that one revision on the notes here. That should have been a 40, not a 55. So it's a pretty big problem that we have to describe, not as big to fully solve, but it puts us also in an awkward position in our notes. I didn't assign a homework set for this particular problem because we're so close to close week. I feel like it's going to compete with reviewing for the final exam. So what I did instead of actually assigning a homework problem based off it, I put down here, let's see, somewhere. There we go. I put down here that there's going to be a version of example 2. Not every single element, since some of these are pretty hard to compute just by hand, but there'll be a new version of example 2, which will be an extra credit question on the final exam. Your final exam score can't exceed 100%, but if you spend time taking a look at this, learning it for the purpose of the final exam, it gives you lots of extra assurances of a pretty high score, so that if you forgot something silly, this extra credit here is going to be pretty substantial. But let's give this a start. Here's where it all begins. Turns out in cryptography, there's lots of interesting kind of conventions that the author talks about in the reading first. Usually we describe people's roles as being just the first parts of the letters of the alphabet. So the person sending the information, and once it's sent securely, is going to be Alice. The person that receives the information is going to be Bob in the setup. And we call, I don't know why you skipped C, probably because it's called the ciphertext. We let Eve be the person who's trying to crack this, who's trying to listen in and decrypt the message Alice is sending. So to prevent that from happening, here's a measure we can take. The plain text is just the original message that's about to be sent. Alice and Bob have to meet together to exchange some information so that they have a secret key that's going to encrypt this. Once it's encrypted, the message M becomes the ciphertext. It's now just kind of meaningless information. Eve is presumably able to actually intercept this ciphertext, but there's a private information here, again, that both Alice and Bob, only those two people hopefully know about, that can be used to decrypt the ciphertext. Once decrypted, it becomes reconstructed into the original message M. So that's our idea. And public RSA encryption attempts to achieve that in an interesting way. But before we get there, we're looking into a quick example called a one-time pad. We're going to be using the exclusive OR operator to show how to do this a certain way, and then mention there is a downside to this. If we reuse this method over and over again, sending multiple messages this way through the one-time pad operation, Eve can start collecting data, zeroing in and cracking our code. If you ever looked into, say, the Enigma machine, the decoding that was done during World War II, that's the kind of sort of stuff that was going on. The encryption was way more advanced than this, but similar ideas. So that's what we're going to give a try. Let's grab this diagram as we go, so we can refer to it. So to start this off, it says Alice and Bob, not Helen, agree on a secret key. So the secret key is this right here, just a bunch of ones and zeros. So 1100 1101. That's the encrypted information, and it's also the decrypted information. It's information the eavesdropper should never have. So the secret key can only be used once, as we indicated. And the message Alice is trying to send is this one right here. Using this method, the size of your message has to be the size of the key. And sure, it's just a bunch of zeros and ones, but that could be a real message, like say, deposit $500 into this account. Who knows what it could be, right? Just written in terms of binary, for example. This one's a pretty short problem, but here's how it goes. Alice is now going to take the message M. It has to be encrypted, so we're on this phase right there. And we're going to produce a ciphertext. This is what Alice is producing before it gets sent out by taking M exclusive OR K. And that's kind of exciting in a way because we've talked about exclusive OR. I think I made a lot of comments. That's kind of a funny thing to introduce here in section 3.2 a while ago. We didn't seem to have a lot of real practical examples using it, but now we do. So it's kind of nice to see this playing a practical role finally. Let's call the exclusive OR operation since it has been a while. Back in section 3.2, here's how it was defined. The exclusive OR, XOR, or using this more of a direct sum kind of symbol, it's going to be true when one of P or Q is true, but not both. So on the truth table here, we have false on the first row because both P and Q are true, but true on the next two rows because one or the other is true, and false here because nothing's true. Just double checking that last bit of information. Okay, so let's take this exclusive OR operation, bring it into our problem, but notice it feels kind of funny. How do you do exclusive OR when K is written as ones and zeros and M is written as ones and zeros? Actually, probably a lot of people in this class know the answer to that. Some people have actually done this in the homework, not by using trues and falses, by just using ones and zeros is how the homework was submitted. I thought that was a great way to do that kind of problem. If you did go that route, what should T be? Should that be a 1 or a 0? 0 for the T? Let's go with that route. So if we go that route, here's our new operation. We have a P, a Q, P exclusive OR Q, and we're going to go 0 for true on that row, 0 for true on that row, and then 1 for false on the last two rows. Then likewise, we're going to go 0, 1, 0, 1. Looking into this one is going to be false, which means this one should output to us another 0 altogether. Hang on. True and true, yeah, that would give us a false altogether. Exclusive OR, it's been a while, I guess, kind of tricky here. Sorry, say again. Thanks you for that reminder on that one. Absolutely a 1. I think I need a key for this one to keep my head straight. Let me write it in right here. Let's put in, for extra emphasis, we're going to define 0 as true, and at the same time, 1 as false. Thanks for that help on that one. That helps out quite a lot. So likewise, over here, we're going to output a true, 0. True on this one, 0. This is false against false, so false again, a 1. And let me fix this spelling on that. So that's going to be the operation we use. And now actually doing this, say on paper, it's going to look like this. Let me write out, first, let's do K. K goes 1, 1, 0, 0. The way we're writing this in is pretty particular. Try to get mono spacing between all the values. 1, 1, 0, 1. Put the message down below. The message is 1, 0, 1, 0, 0, 1, 1, 1. And now C, the ciphertext, will be defined as M exclusive OR K. So we're ready to go. If we see ones doubling up, we have false with false, so false again. But if we see this, a mismatch between the 0 and the 1, we have a true, so we convert this one to a 0 for true. And that's the name of the game. We want 0, 1, 1, 0 to get our zeros. If it's 0, 0, this one comes out as a false for a 1. 1, 0 here gives us a true, so 0. 1 by 1 is false, so 1 again. True here for 0. And false here for a 1. Let's double check that. So false, true, true, false, because of the double true. That's because of the exclusive OR operation. Then true, false, just double checking the coding there, and true, false. I think we've got it. Does that look right to folks so far? Okay, so this is the ciphertext C that gets sent out. So there's a message. Who knows what this is really representing, but it's got to be a secret. So what actually gets sent to Bob, maybe over a text message, something that could potentially be intercepted, is this ciphertext. That's what he gets, but has no understanding of what's really being sent until the decryption happens. But the decryption's kind of nice about this. Notice all we really did is kind of flip the bits in a certain way. If we do another exclusive OR with K, that's this operation, we just undo the operation itself. So it's a kind of inverse all in one. So the message that's up there, we'll take another peek once we complete this and see if we're close, is going to be reconstructed plain text, decrypted by saying M equals, like me actually write down the cipher just above so that we can be really sure we've got it down. So first the ciphertext is 1, 0, 0, 1, 0, 1, 0, 1. Now down below, we'll use the decryption key and say plain text message, now totally unsecure, is C direct sum. The security key, once again, K. Here's K up by the red dot. 1, 1, 0, 0, 1, 1, 0, 1. And now this is going to be, oh, let me put down, kind of messed up that table. That should have just been a K. And then down below, really following that same process, we have message, C, exclusive OR K once again. And here's how it's going to go. Let's reveal the table just for extra guidance if needed, or more importantly, is the true false is what I wanted to see. So 1 and 1 gives us a false for a 1. Then we have true here. This is true with true, so false on that one with exclusive OR. Looks like true and true on the next two. So that's going to be 0, 0, false on this one, false on this one, and false on this one. So I have a 1, 0, 1, 0, 0, 1, 1, 1. I'm not sure if that's quite right. Let's double check. Hey, it is actually 1, 0, 1, 0, 0, 1, 1, 1. For some reason, I thought I went 1, 0, 1, 0, but that was maybe that I was thinking of. We've got it, folks. We were able to reconstruct the message. However, if there was an actual eavesdropper, they can start collecting more and more ciphertexts. The author is kind of vague about this, and then use frequency analysis to now figure out what K was and begin decrypting all messages. So that's the danger about this kind of process, and that's why the author calls this encrypting using the exclusive OR operation a one-time pad, coming back from, I guess, espionage back in the day. This can really only be done with total security one single time. What, any questions, folks, about the whole process of the cryptography in this diagram? Okay, now next thing we want to get into is the public RSA security system encryption for encryption. So here is the RSA crypto system next. The backbone of this is that it's really hard to factor numbers. So here's a couple thoughts before we get right into this. If I take P is prime, and let's say that P is greater than maybe 10 to the power, let's say 30. really, really large prime here. Likewise, Q is prime. Let's maybe not make the order of magnitude unrealistic. Let's go power 20. I should have looked that up before I threw in some wild numbers. But we want some really enormous primes with hundreds of digits, essentially. So let's take Q to the power of something larger, 10 power 20, something like that. And set n equals P times Q. Once we do that, P times Q is a very, very large number, order magnitude around 10 power 40. We bump up the size of these even higher. This could be around 10 power 50, maybe 10 to the power of 100, if our systems can handle that size. At this stage, multiplying P to Q together is the easy phase. If you've taken calculus, that's kind of like differentiation. It's direct, there's a process done just by following the algorithms. So this part is easy. Now let's imagine, suppose n is known, P, Q are unknown. If that's the case, I didn't think about my space here. Let me kind of bring this a little bit higher. If this is a case where we have the value of n, once we multiply them together, being the knowns on this problem, while I quickly delete. So if we know what n is, some really, really large integer, but for the sake of security, it's been hidden what the original P and Q are, then it is very demanding computationally to find PQ. Not impossible. There are integers multiplied together. They're primes, so there's not a lot of factors in this number n. Exactly 2. It's a gigantic number, and to really crack it, what are the two primes P and Q takes an enormous effort. So that's the major idea of what's going on with RSA encryption, decryption. There's a lot more details, but that's the backbone behind it. Again, if you're taking calculus and you're thinking about differentiation, this is like the differentiation phase, just multiply P by Q. The integration phase, unwinding stuff, is trying to take your n that's known, factor it down to P and Q. That's the hard stuff. Integration is a wild process. Lots of things can go wrong. And so that's the same kind of thing that we're doing here in Spirit as well. So just like we did look into the last problem, the components are going to be key generation, the encryption phase, the decryption phase, and down below is the specifics on how it all goes very next. So Bob chooses two large prime numbers, P and Q, and defines n as P times Q. So that's going to be our major idea. Then we do a lot of other interesting operations. We have to choose E so that we have something relatively prime. We can use our Euclidean algorithm to detect relatively prime. We have to also take something like this. D is going to be inverse mod P minus 1 Q minus 1. We can use our inverse algorithm to discover the value of D. And then once that's done, Bob is going to publish ENN as his public key. Everybody can look this up, including the people who might want to eavesdrop and figure out what the security message is. But he has also the secret key, DN. D, defined this way, is really, really hard to crack because in order to find D, you have to factor n. Once n is factored, you'll take E P minus 1 times Q minus 1 and find the value E. But E is not even unique. You can pick E to be really anything that qualifies for relatively prime. So this imposes yet an extra challenge on all of this, giving us greater security. This isn't total security, but the process of encryption is like n times p. It's pretty fast, other than a couple things like doing some modulus operations. However, trying to crack this is so demanding computationally, it gives us the sense of total security. We have security through just the impressive amount of computation power it would take to crack this, even though all the tools are available publicly to do that hack. That's kind of interesting in a way. So that's the backbone of the RSA crypto system. Lots of other details. How does decryption work? More mods goes on with this, and this is the difficult one we were alluding to. But the diagram is the same. What we're trying to achieve is not too different, just a different way to encrypt. So Alice will encrypt a plain text M using the public key that Bob has to generate and publish to everyone. Then this goes out, the ciphertext. This gives the formula in computing the ciphertext. Now, Eve can pick this up. However, if Eve is going to do anything with the ciphertext, that has to happen. Factorization of N into PQ, discovering the right value of E as well, and that's a lot of effort. Probably by the time that's solved, the relevancy of this information has long been passed, maybe by years even. But now Bob has this ciphertext. He uses the secret key over here. This is the one that's not published to anyone whatsoever, and reconstructs the plain text message M in this way using modulus. So quite a bit different than the one-time pad, but extra secure now this time. This can be reused over and over again using the same public key, the same secret key, or these could just be changed out as necessary to increase the security. Well, any questions, folks, with the schematic of what's going on here? Okay, we've gotten to the point where this can't be a homework problem since we're out of time to assign homework in a reasonable way that doesn't compete with the reviewing for the final. But elements of example 2 are going to be potentially extra correct question like we mentioned. Now, let's start this off. I'm going to we'll take some screenshots as above as necessary for each part. So keep that diagram in mind or just available, ready to look at. We're going to deal with these primes. And sure, they're not very large, but this is just an example to illustrate the RSA crypto system rather than generating some primes that could take a lot of memory on this computer just to store. So the primes are going to be 5 and 11. This is just a reminder, these are ginormous primes in the real system. First thing we're going to say is, what is Bob's public key? That's what's going to go right here. And Mary has to use that, Alice has to use that to encrypt. And what is Bob's secret key? That's over here, and Bob has to use it to decrypt Alice's encrypted ciphertext. Let's scroll up here for just a moment. Here's how Bob does both things at once. This is the key generation phase down below. So maybe go down to this part here and give this a try. First thing we want to do is define N in this way. So N will be defined to be P times Q, so 5 times 11, for 55. So we have the N phase down. Easy sailing so far. Next, we look into this. Sometimes I think our textbook also mentions this. This is referred to as Euler's totient function, if you've ever heard that come up before, but he doesn't really refer to it too much beyond that. So let's just use this result right here as we see it. We're looking for a value of E, and it cannot be 1, so that we have relatively prime between E and P minus 1 times Q minus 1. So let's just say our want over here. We want E to satisfy greatest common divisor of E against P minus 1 times Q minus 1. It has to be equal to 1 if we say relatively prime. So this is going to be the greatest common divisor between E and P minus 1 is going to be 4. Q minus 1 is going to be 10. So this is greatest common divisor, E and 40. Multiple values of E will work. We'll pick the smallest one just so that the computations are a little bit easier by hand. But anything that satisfies that is going to solve this for us for our E. Let's set below, set E equals, and you might already have a value in the back of your mind. Factors of 40 are 2, 5. You know, that's about it. Just 2s and 5s, it seems like, for factors of 40. That means setting E equals 3 would do the job for us. But if we had some nastier numbers, we could have also done, say, this way of looking at it. For looking into the greatest common divisor, we could just as well use Euclid E40. So back over here, let's call Euclid. Again, we might start at 2. That's the first valid value. E can't be 1, it has to be an integer. But that does have a greatest common divisor of 2. Moment we go up to 3, yeah, that's relatively prime. Greatest common divisor is 1. And we can just stop right at that step. Let's take E equals 3. So setting equals 3 satisfies this phase right here. Part 2 is now complete. So we have an n value. We have the value of E. That looks like an important one to track. So let's keep that one highlighted. Now that we have E, this is the next phase for us. We need to find the value of D. That one looks pretty important as well. That's going to be the inverse of this, mod P minus 1 times Q minus 1. That's going to be the 40 that we see here. So next operation, set D to be equal to E inverse, which will then be equal to 3 inverse, and this is happening mod P, or in Z40 rather. Here's our algorithm from section 7.4. Let's indicate here. Use inverse. And I think we describe this as something along the lines inverse AN is the syntax typically used. The n value here is the Z40, so the 40 specifically. So inverse, and this will be 3, since we're calculating 3 inverse. Next value will be 40, since we're in Z40 for this problem. And hang on, yeah, P minus 1, Q minus 1, give us the right 40. That's a mistake I meant to made right here on the notes in red. Mixing up the n and the P minus 1, Q minus 1, I think is kind of easy in this problem. At least it was for me, I think. And claim is 27. That means we have some really interesting computations to maneuver through. But this is kind of par for the course. The more you try to make this an easier problem, the more just frustrating it gets. You just have to be satisfied sometimes with interesting modulus computations at the decryption phase. So D is equal to 27. Let's check that out. If we take mod and div, take 27 times 3, because we claimed 27 is the inverse to 3, in, where should it be? Let's see here. The inverse was found in Z40. So we're looking for an inverse in that same place. And I forgot to highlight just the first output. The output is 1, so yeah, 27 times 3 mod 40 is exactly 1, indicated down here, which means this does verify we've got the right inverse. So the inverse is done, and now Bob is ready to go. We're going to publish 2 things. Well, excuse me, publish 1 thing. This goes out to the public, EN, but D is the secret key, kind of like the K when we were encrypting and then decrypting the ciphertext in the last problem. So here's the final part of part A. The public key is kind of interesting way that it was written. Let's just keep that notation. Bracket 3, comma 40. Oh, hang on, not 40, right? It's N being indicated there. N is 55 now. That's one thing, again, that's kind of confusing. Sometimes we're using P minus 1, Q minus 1. Other times we're using just P times Q. So that should have been a 55 right here. Next, the secret key. This has to be used by Bob to decrypt the ciphertext is 27 for D and 55 again for N. I'll leave this bit right here just to match up the highlighting with what we just calculated. But that's the first phase in the RSA encryption process, or crypto system, better way to say it. Any questions at all, folks, getting to this stage? Okay, and you can imagine if you had the time and the energy and we had more weeks in class, we could probably just code up this whole kind of process as well. Except that you have to be really careful when you go to the decryption because the standard modulus operations don't quite work the way we'd like them to. But part A is done. Now comes in part B. So with an extra remark on the fact that we had small primes to make this a by hand doable problem means we have one extra challenge we have to maneuver through first as well. But first, here's the other part of the story. Alice needs to send Bob the plain text message 5720. We're going to imagine, just to give some color to this problem, it's the PIN number to a lockbox in some high security bank. Not saying there's any espionage going on. Maybe there's pure permission to do that. But we need to open this high security box, or at least Bob does. However, we can't just send a PIN over a text message or over the internet totally unsecure. So we want to know, what is the encrypted message? That's plain text 5720. The ciphertext will be the encrypted message. And here's the extra challenge. 5720 is a large amount of information to send out when P minus 1 times Q minus 1, should have deleted that N right there. We'll have to make a change on the notes. Should have just been P minus 1 times Q minus 1 is 40. We would want a number right here larger than that, but it doesn't mean all hope is lost because we can now just send out 4 encrypted messages. We're going to encrypt the first, second, third, and last digit. So now the message is broken up in this way. So here's the plain text message. C1, C2, C3, C4 will be the encryption of each one of those digits. We want to know what is the cipher message being sent to Bob. So we're going to turn up. We're sending that phase right here. And let's grab this information from now the encryption phase. Okay, let's give this a try next. So Alice finds Bob's public key is what it says next. It's written in as eBob and Bob, but subscripting there is kind of a lot to read through, but we're just referring to that, 355. To send the message, and we have several messages to send, one per digit. The computation is going to be C equals M to the power of E mod N, where E and N come from the public key. So we'll start with just citing that public key. Bob's public key is bracket, let's say here, 3 and 55. Let's keep the color coding going just to see the role of each of these values. Okay, we've got that information cited, so hopefully less scrolling for the last bits. So we have looked up the public key. Now we have to compute C1 through C4 in this way. Let's just write it out as our own formula. Ci is going to be mi time to the power of E. So that's the eBob being mentioned right here, mod N for 1 less than or equals to I, less than or equals to 4, just saying do the same for each one of those values. So it looks like we're ready to get started. We're still on phase 2, but we can say M1, following the information over here, is going to be equal to the first block in the pin, which is the digit 5. We want to disguise this from the world, so we're going to raise this to the power 3 mod 55. And this is not the bad modulus phase. These are pretty standard and routine to run through. It's the decryption where it gets interesting. So let's just take advantage of some extra speed on this one and save our energy for the harder ones. Let's run mod and div 5 power 3, 55, giving output 1, the modulus. So 15 on that one. So that is a mistake right over there. I shouldn't call it MI. I should be calling it C because we're building the ciphertext. So let me call this C1. Okay, so next, C2. Same as before, look up digit 2, 7. Raise it to the power of E, which is 3, mod 55. Then fast computation over here, just go 7 power 3, mod 55. We've got a 13. Next, C3. Third digit is 2. 2 power 3, mod 55. Okay, that one's pretty fast, right? Anyone see what this one ought to be? Good call. Ought to be 8 from class. And now the last one might make you kind of concerned when you really look at what's going on in RSA crypto system, because this system is really deployed across the internet for security. C4 means take the fourth component, which is a 0, but 0 to any power is still 0, mod 55 is still 0. That means selecting 0 didn't actually give us any security down here because 0 itself is still part of the ciphertext. That ciphertext could be intercepted right over here by Eve, and now Eve has leverage against us. She knows a little bit more than what we would like about this kind of problem. It's almost kind of chilling in a way, except this is a textbook version of public RSA encryption. There's extra things that I think they say padding algorithms that account for this problem right here. So if there is a 0 as part of a message, other things happen to kind of obfuscate that, to disguise the fact that it ever was a 0. Then it gets ran through RSA decryption, encryption phases. And so we don't have that weird problem right here. But in the textbook problem, we definitely do. And so Alice is going to transmit this message. The transmitted message to Bob. This is not the plain text, so we don't know the pin yet. Well, Bob doesn't, we do. It's going to be grab all these values, reconstruct it much like the message was. So in order, it's 15, 13, 8, and a 0. So that gets sent out, and now we're on to the next phase in this process. But any questions so far, folks, with how it's working? Okay, so here's the next part of the drama. Bob is at the bank, vault, ready to open the lockbox. He receives the ciphertext C, from Alice. So this is what he receives. He may already know if this is the exact security we're using. 0 is part of the pin, as does the eavesdroppers. And now he must decrypt the total message. One of them is a freebie. That 0 decrypts right back to 0. But once it's decrypted, we'll have the plain text message and be able to know what the pin is for the lockbox. This says, just as advice, take advantage of Theorem 7.4 in section 7.2, as well as mod and div all at the same time. We're going to use all tools to leverage against this problem for the decryption phase. So let's also grab the information. We're right here on the diagram, so the message has gone out. And now Bob has the ciphertext C broken into 4 components. And Bob is hopefully the only person on the planet with the secret key stored on his machine or wherever this might be stored. So we have to use the value of D once again. And this is how it's decrypted. One step here, but it's a heck of a step. And we have to do it essentially 3 times, but really 4. So let's give this a try. So Bob computes M. We're getting the plain text message back. C to the power D Bob, mod N D Bob, where D Bob N Bob is Bob's secret key. Again, that's some interesting subscripting, but it gives us a good idea how to start. Let's just look up the secret key again. The secret key is bracket, I think this was 27, and then 55. 55 is not the secret part of this. That already got published with the public key. The 27, though, that's what we needed to decrypt this. We also have the ciphertext. Let's pull that down so eliminate some scrolling. C is 15, 13, 8 and 0, defined to be C1, C2, C3, and C4. So let's give this a try. You have to do this 4 different times, so I guess that's some really good practice. Here's the equation that's going to be used. M1, this is going to be the first digit, is going to be equal to C it refers to, but that's now going to be C1, referring back to 15. To the power of D, it now says, that's the rough part right there, because we're taking 15 power 27 mod. Over here, when it's mod N, we're referring to that 55. So mod 55. First, let's see what this system might say. I wonder how other languages compare on the performance of this, but this language does not like this at all. 15 power 27 mod 55. Another probable complete loss of accuracy in modulus. So again, a wonderfully vague and concerning statement all at once. But we can break this down. In fact, this is where, if we had enough time, the Chinese remainder theorem comes into play. You could factor 55 into 5 by 11 and solve 2 related smaller problems and then just bring them together. But in the sake of time, we're going to do this in a slightly different way. The advice is go back to section 7.4. So here we are. Hang on, let me double check what that said. Theorem 7.4 in section 7.2, that was a wrong spot. So back to that same theorem. Really, what we want is just part 4. But let's just cite the whole theorem just for emphasis on the notes. And let's see how to handle this. The power is just too large at 27. But 27 can be factored as powers of 3. So we have 3 cubed sitting right there. Let's go big. By going big, what I mean is, let's put power 9 right into that spot. So let's write this as 15 mod. Actually, let me do one extra step just to organize how we're rewriting this. This can be re-expressed as 15 to the power 9 to the power 3, since these exponents would multiply together, mod 55. But then, now look down to part 4 of this theorem. This can be re-expressed again as 15 power 9 mod 55 to power 3 mod 55. So the 15 power 9 is taking the role of A. The 3 here has a special role as well. The 3 is the B that we see down below here. The blue color coding now has different meaning on this problem, or this part of the same problem. And the K is just the N 55 we're taking. So the problem 15 power 27 was way too big in order of magnitude to compute. But we cut it way down right there. Let's take a look into 15 power 9 mod 55. That's just a 25. And if we try it over here, I'm not too sure if this is going to work for us. You know what, we better not try. Even if it does work, there could be a lot of computation time just on that algorithm there. It wasn't meant to be the most efficient algorithm in the world. So let's be settled with 15 power 9, whatever that number is. That number, mod 55, it's just a 25. So we have, let me try again here, 25 to the still exponent 3, mod 55. And that's a way better problem, 25 power 3, still a large integer, but we can deal with that. 25 power 3 mod 55 comes out as exactly 5. Sounds like that's a right number to our first pin. Awesome. So our message was originally 5. So yeah, we got our first one down. So really, Bob just needs 2 more. Needs to decrypt this one, decrypt that one. That one will take as a freebie because it really is. In this process, it would just be 0 power 27 mod 55 back to 0. But any questions at all, folks, with this interesting way of doing modulus? Okay, let's try it out all over again. M2. M2 means we have to go to second part of the ciphertext, 13, raised to power 27, mod 55. And we were always raising it to power 27. So if this strategy worked once, it should work twice. I'm just going to copy this method. Let's rewrite this as now 13 to the power of 9 to power 3, mod 55, which then becomes 13 power 9 mod 55 to the outer exponent, power 3, mod 55 again. Now, this is a part where we'll use some technology to calculate that modulus. And I mentioned on the final exam, there'll be certain elements that you'll calculate for extra credit. Maybe not this part, because you'll notice we're still using technology to take advantage of even this right here. So you're going to be looking into some of the easier parts computationally in this system. So 13 power 9 mod 55 comes out as a nice 28. So it's becoming a 28 power 3 mod 55. Another computation here. 28 power 3 mod 55 comes out as a 7. And again, I think we're on the right track. Let's take a peek. I mean, Bob can't do this. Bob just has to be really hopeful that he's doing it right. But that's the right digit, 7 on this one. So if we can get a 2, we are home free on this problem. Well, any other questions so far, folks, before we launch into essentially the last one? Okay, so here we go. M3
I have
for the
a
third.
question.
Yeah, go ahead.
How is 139 mod 55 28? That doesn't compute in my brain.
Oh, yeah, that was my bad there. That should have been 13 power 9, not 139.
Oh, okay.
Yeah, so that was that outer exponent or inner exponent 9 right there. So it's poor penmanship. Sorry about that confusion. Any other questions at the moment? Okay, let's go again at this. Now we're going with 8. So it's kind of lowering in complexity as we go. That's kind of nice. Just an accident with this problem. This is going to be 8 power 27 mod 55. And you know that base is at least small enough. Let's test the technology here and see if it can handle this one. 8 power 27 mod 55. Now it's still too large for this system to handle. So let's try this again. Now, same process as before. We're going to factor the power 27 as a 9 by 3. So this will become 8 power 9 to power 3 mod 55. Then that didn't make the problem easier until we used part 4 of this theorem 7.4. So we're going to rewrite this as 8 power 9. Again, that's bad penmanship. 8 power 9 like that, mod 55, to power 3, the outer exponent. That result, mod 55, will lower the complexity of the problem in a major way. But that's still difficult. So let's treat ourselves to technology so we're not here for too long. But if you had to do that by hand, just keep using the strategy. You can rewrite 8 power 9 as 8 to the power 3 to the outer power 3, and just keep doing this over and over again. Our author actually shows how to do that on paper. It is quite a long computation. So we're streamlining just this part right here. 8 power 9 mod 55 comes out as exactly 18. So this problem is now 18. The outer exponent is still right here, also expressed. Oh, just expressed in that way. Got a little bit mixed up. Once we do the modulus part, the thing in the parenthesis became 18. Outer exponent is still 3, mod 55. And you know what? I think the mod and div algorithm could handle that. Let's see if it would really work on that one. So here's mod and div, 18 power 3, mod 55 is exactly 2. And yeah, 2 is the penultimate digit. So we have essentially all of our digits. And let's just write this out for the sake of parallelism. The last one is a freebie because M4 would become 0 to the power 27 mod 55. But that's still just a 0. So this tells us finally the pin is M, reconstructed as all of these digits, 5720. So that's the process of the RSA cryptography system. Kind of a weird one, but again, that's the idea of what's going on here with the decryption phase. That value of D came from P minus 1 times Q minus 1, and it's an inverse. And then P and Q itself in the real deployment of the system are massively large gargantuan primes. That makes this kind of system essentially undefeatable. But our author has some pretty interesting words on the last part of the section. There are active attempts to try to crack this. It may have already been done and no one seems to know about it yet. If someone cracks this system, they're not going to just announce that. They might cleverly just keep that as private knowledge used only when really, really necessary or when it benefits them the most. So that's kind of an open question. Is there a way to make the computation of D at 27 a lot more quicker than we think it can be done? Or is this still, in 2025, a really secure problem? We're not quite sure at this point. But that's the good news with public RSA encryption, that it looks like it's still pretty secure as a system. And this weird portion where 0 seemed to be a security issue is also fixed by padding up the system so the number gets fudged, and this becomes a non-zero value. But it looks like we did it, folks. That's the end of this section here. The closing remarks are just information tying together what role does the lemma, excuse me, not the lemma, Fermat's little theorem play. Its role is to prove this lemma, which is then a bona fide theorem that tells us the process of taking a public key, constructing a private key, and then this decryption will always work. And then further comments about the security and the other problems that could go on. So I'll leave this as just additional reading at the very end. But it looks like at this point, folks, we have concluded with all the content of the course. This is going to be converted to an extra credit question on the end of the exam. If you want to give this another try, I'll be happy to generate different digits, let me know. Otherwise, we're now in the review side of the course. Maybe not today. We'll have, when we go back to the Moodle website, when we come back to the closed week, I'll start publishing extra information for review problems, that kind of work. And just like any other of the exams, I'm going to say what the definite coverage is. It's comprehensive, but we'll say it in a better way than that. And provide final exam review materials down below. But any last questions, folks, in our last 5 minutes? Okay, we'll call class a little bit earlier than today. Have a great night, folks, and a great weekend. And thanks for all the help with the syntax errors and coding bugs that we encountered along the way in this chapter 7. Definitely was kind of a fun one, but one you have to do really carefully, I'd say. But have a great night, folks. I'll talk to you all later.
Obvious how this works, or is it kind of just like a how-to to kind of demonstrate?
More of a how-to, yeah.
Because I was like, I get the steps we took,
Mhm.
but I don't get why it works.
Gotcha, yeah. The why it works is really interesting in the sense that down here it goes on to say the system is not defeatable. It actually doesn't work in the sense that there's total security here at all. It's just for this to be cracked, you need way more computational power than really exists currently. At least that's our assumption at the moment with it.
But for all the private people who keep to themselves.
Right, yeah.
In Dan's class, and he was like, mathematicians would just keep the knowledge to themselves and then go to competitions to like solve
Yeah.
things really fast. And I was like, that's weird. Why would math be private information? But now, like, it literally is.
Yeah.
So,
One example of that would be L'Hopital's rule. That was purchased by someone, and then that person used it to solve problems, write an actual textbook, and all sorts of stuff. And another example is these kind of algorithms are definitely trade secrets, not just among corporations. But if you think about the NSA, for example, the National Security Administration, they undoubtedly have a whole slew of different tools, algorithms that are amazing computer science that deserve to be shared to the world, but it's weaponized knowledge that they don't want to release. They would rather kind of sit at a higher precipice with all that extra knowledge all to themselves. It really is, yeah.